Live. Hi everyone at home, welcome back and welcome to the final the final open evening from Cambridge University Astronomy. It's been a really crazy season and it's been really nice to be able to take these things online, and thank you so much to everyone at home that has been watching and enjoying. It really means a lot that we have been able to carry on our normal series of public talks and take them to a new audience, like people that might not normally have been able to come to Cambridge and watch these things. We will carry on streaming these on YouTube in the new season. So, we will have our fingers crossed very hard that in October, we're going to be going back to being in person and doing our talks in the lecture theatre. But our lecture theatre is now fully equipped for YouTube streaming. So those of you in different parts of the world that can't make it to Cambridge will still be able to enjoy these talks on Wednesday evenings from October. So there will be no stargazing tonight because those of you in the UK can look out the window and see that it is daytime. So we're doing these after the clocks have changed. So while there's no stargazing, we're going to more than make up for it with our fantastic final headline speaker of the evening, Dr. Gareth Jones from Cambridge University. And he's going to tell us all about the distant and dusty universe. So over to you, Gareth.
Righty, thank you. And yeah, howdy everybody. Thanks for tuning in. And so I'm Gareth Jones. I'm a postdoc over here at the University of Cambridge. And tonight I'm really excited to be able to tell you about the distant and dusty universe. So one of the first things we should talk about is distances. And one of the really cool things about astronomy is that when we talk about distances, we're talking about really big distances. So to put this in scale, we can think about the closest thing to the Earth in space, which is the moon. So we have the Earth and the moon here, but these aren't really to scale. We know the moon's a little bit smaller, a little bit farther away. So if we do put this to scale, we can see, the moon is tiny and really far away, farther than the distance from North America to Europe times a lot. So if we put some numbers to this, the Earth and the moon are around 384,000 kilometers apart, or 250,000 miles, which is just a ludicrous distance, I think. And I can't really hold that in my head. So let's imagine that you can drive a car from the Earth to the moon, and the Earth and the moon just stay where they are, and your car drives on a rainbow road, and you just floor it. You go 160 kilometers per hour, 100 miles an hour, and you just go with no stops, no restroom breaks or anything. How long do you think it would actually take you to travel all the way from the Earth to the moon? Probably more than a couple hours, maybe more than a couple days. Turns out it would take around 100 days of going 100 miles an hour just to get to the closest thing in space. So that's a really long time. So we can think about something that's a little bit faster. We can think about light. And light travels at the speed of light, which is around 300,000 kilometers per second, which turns out to be 1 billion kilometers per hour. So light is faster than a car by a little bit. So how long do you think it will take light to travel from Earth to the moon? Turns out it only takes around 1 second, just a little bit more. So instead of saying that the Earth and the moon are 384,000 kilometers apart, which takes a long time to say, it's a big number, we can say they are 1 light second apart. So here, light second is actually a distance. So it's the distance that light travels in 1 second. So it's not a unit of time. So we can do the same sort of trick for some other, relatively nearby objects. So we can look at the Earth and the sun. And the sun is about 8 light minutes away from the Earth. So 8 light minutes is more than 1 light second. And now we can look at the closest star to the Earth outside of the solar system, which is called Proxima Centauri. It turns out this is around 4 light years away. So that's a really long distance. We just talked about how fast light travels. And this is where things get really cool, because by looking at these really far away objects, we can actually do a little bit of time travel. So to explain this, we just talked about how Proxima Centauri is around 4 light years away. So that means that if some light leaves Proxima Centauri in 2017, it's going to travel and travel and travel, and it'll take 4 years to reach Earth. So it won't reach Earth until around 2021, or this year. So if you go out right now and you go to your giant telescope, which is on the Arctic Circle or whatever, and you point the telescope at Proxima Centauri, the light that's coming into your telescope came out of the star in 2017, so 4 years in the past. So really, you're seeing that star as it was in the past, which is really cool. So we can actually look back into what objects looked like a long time ago. So we can go even farther. We can go outside of our galaxy, the Milky Way. We can go to the closest large galaxy, which is called the Andromeda Galaxy. And it turns out that the Andromeda Galaxy is around 2.5 million light years away. So that means that when you look at Andromeda, you're seeing it as it was 2.5 million years ago. Of course, space is even bigger. So we can talk about a couple other ones. And these are even farther away, so we don't have cool names for them anymore. They just have numbers and letters. So this first one, NGC 2525, is around 71 million light years away. So when the light from this galaxy left, and that we're seeing right now, dinosaurs were still around, pretty sure. We can look at an even farther away one, UGC 1693, which is around half a billion light years away. So 500 million light years, which is really far. And we can go even farther. We can look at the farthest away galaxy that we've ever observed. And to show you how far away this is, we're going to look at this little movie that's going to zoom in and show you where this is on the night sky. And just keep in mind that as we're looking at these really far away objects, they're going to look even smaller and even fainter just because they're really far away. Just think about like a flashlight that's on a hill that's a mile away. It's going to be tiny and faint. All right, so it's going to zoom in on the Big Dipper. It's going to show you Ursa Major and the picture of a wombat for some reason. You might think that's a bear, I'm not sure. All right, we're going to start zooming in. So a lot of these little dots are stars. Some of them are galaxies. You can usually tell by the shape. We're going to be zooming in for a while here. These are all really tiny. And there's that little red dot. And we're going to zoom in on that red dot. And there is a beautiful picture of the farthest away galaxy, which has the really catching name of GNZ11, which I think is really actually nice, but it's up to you. So this is the farthest away object that we've ever observed. And from observing this object, we are pretty sure that the light has been traveling to Earth for 13.4 billion years. And the universe right now is only around 13.8 billion years old. So that means that when this light that we're observing left this object, the universe was only around 400 million years old, so less than 500 million years old. So 400 million years is a really long time when you're talking about people or dinosaurs. But compared to the age of the universe, this is a drop in the bucket. So this means that when we're looking at GNZ11, we're seeing this galaxy as it was when the universe was practically an infant, which is really cool. So this kind of brings up a really interesting point, though, because when we're looking at these really far away objects, we need to keep in mind that there's sort of two different universes here. There's the observable universe, which is everything that we can see. And so this includes, we can look at the sun, we can look at the moon, we can look at Andromeda, we can see this light that's coming from GNZ11. But when we're looking at these really far away things, we're looking back into time. And so there is actually an edge to the observable universe. We can't see past like the first few 100,000 years of the universe. There's just really nothing to see. On the other hand, there's the physical universe, where there's just galaxies all over the place, and it's pretty much homogeneous. Anywhere you look, it's going to be pretty much the same. So when we actually look with telescopes, we're looking at the observable universe, and by looking at different distances, we're looking at different times. We can kind of build a picture of how the universe looks now and how it's evolved, and from that we can build a picture of the physical universe. But we can't actually see what the physical universe is. Because we can't actually see what GNZ11 looks like now, because the light from the galaxy now is just leaving, and it's going to take a very long time to reach us. So by looking at the observable universe, we can actually kind of build a really cool picture of how galaxies have evolved and how they've affected the evolution of the universe itself. So this is a nice little picture here. So we have the Big Bang at the top, and we have the current day at the bottom. And time is evolving as we go down. And after the Big Bang, everything was really complicated. I was kind of going to skip that. If you saw Chandrima's talk a couple of weeks ago, yeah, you already know about that. So, I mean, a few 100,000 years after the Big Bang, everything was still really hot. All of the matter was so hot, it was just like in this ionized plasma soup, and light was sort of trapped inside of it, couldn't escape. But eventually, the space expanded, and things were able to cool down a little bit. Light was able to escape from this soup, and then things were able to form molecules and start gravitationally collapsing. But it was still some time until the first stars formed, and so there were the cosmic dark ages. And then the first stars and galaxies started forming around 500 million years after the Big Bang. And these stars and galaxies were still sort of encased in this really dense gas that was blocking the light from escaping. And so by shining in ultraviolet radiation, they kind of carved these bubbles in this gas. They sort of heated it up so that light could actually travel. And this process of carving out these bubbles was called the epoch of reionization. And by 1 billion years after the Big Bang, all of these bubbles sort of merged with each other, and the universe became transparent. And in this picture, it shows that the universe between 1 billion years after the Big Bang and 13.8 just evolved normally, but it's a bit more complicated than that. But the cool thing here is that we actually can look at galaxies like GNZ 11, which, as we talked about, we're seeing this galaxy as it was when the universe was only 400 million years old. So we can actually look at the universe way back then. And we can also look at galaxies that are really close to us, like Andromeda, and the other galaxies that are a few 100 million or maybe a few billion light years away. So by looking at these faraway galaxies, we can directly see what's going on. And I'm going to switch to the next slide, which is kind of bright, just to warn you. But we can also compare our observations to simulations. So this is a really cool simulation of a giant volume of space that has some gas in it. And it's going to go from around 500 million years after the Big Bang to the present day. And just start it there. So you can see that, in the early days, gas was organized in these filaments. And over time, these filaments sort of, collapsed together and merged. And it was a really complex structure. This kind of looks like, some neurons, if there's any biologists out there. So now we're about 3 billion years after the Big Bang. And so now you can see that it's not just a bunch of gas. Now there's a bunch of these really bright galaxies where the filaments have, kind of collided with each other. And all these little point sources out here, it's kind of hard to tell with the scale, but each of these are actually galaxies. So we have these really bright clusters of galaxies, and there we have a big, outburst of gas because two galaxies ran into each other and spit off a lot of gas. Got some more outbursts out there. So we're almost at the present day, and each of these little points is still galaxies. So you can see that this is a really complex sort of situation. These aren't just galaxies that rotate in space for 10 billion years. They're colliding and finding a lot of gas and evolving really well. So I have to give major props to the team that made this. It was called the illustrious TNG team. But just I'm going to flash back to the early days versus now. So there's a lot of evolution that goes on, and it's really complex. And this simulation was made to create these bright cluster galaxies, and they have other simulations to make less crowded volumes of space, but this one's the prettiest, I think. So the next question is, we can make these cool simulations. We can look at these galaxies that are way far away, but how do we actually see these galaxies? We don't just get our telescopes out and go in the backyard and look at them. We have some really cool instruments that we use. My favorite, I think, is the ALMA array. So it's the Atacama Large Millimeter Submillimeter Array. And it's a set of radio telescopes in Chile in the Atacama Desert. And they all look at the same point, and they absorb low energy light. So they observe low frequency radiation. We also have the HST, Hubble Space Telescope, which you know about. This is in space and looks at visible light. And this one's really cool because it looks at a relatively large field of view, and based on the light it gets, it can actually figure out how many galaxies there are that are really far away. We have the VLA, which is another favorite of mine, the Very Large Array. If you've seen Contact or all the Terminator movies, you've probably seen it blown up before, at least in Terminator. So yeah, the Very Large Array is kind of like ALMA, except it looks at lower frequency light. And then for fun, here we have the Chandra Space Telescope, which looks at X-ray light, and it's obviously in space. And there are many, many more. There are thousands of telescopes in space across the world. There's some in caves or underground. There's some underwater. So the next question that you might be wondering is, why do we have so many telescopes? Why don't we just build one giant one on the moon, or maybe build one in space? And to answer that, let's have a quick little analogy here. Let's say that you're walking along a street and there's a row of houses, and you hear some sounds on the other side of the houses, but you can't see through the houses, but you want to know, what's happening over there. The issue is that you can't hear all the sounds at once. You can only hear high frequency sounds, medium pitch sounds, or low pitch sounds. So if you can only hear high pitch sounds, you might hear some birds and say, oh, there's a cardinal, there's a blue jay. So maybe we're like in a forest or something. If you can only hear medium pitch sounds, you might hear some people talking or a dog barking or a turkey. So you say, oh, well, there's people over there. That's cool, but there's a turkey. That's weird. Maybe we're near a farm or something. And the low frequency sounds might be a train rumbling by, a van, the engine of a tractor. So you can say, well, there's a tractor, so there might be a farm, but there's a train. So this isn't like, there's some connection to some other cities. So if you can only hear one of these pitches, then you might think that you're in a forest or a weird town where people keep turkeys as pets. But if you hear all of them, or by combining all of them, you can tell, oh, we're probably near some sort of big town that has some farm stuff nearby and has a train. So you get more information by combining all of these different frequencies. And the same sort of thing is pretty much true for space. So here we have a bunch of pictures of the center of our galaxy, the Milky Way. And we have low frequency or low energy light at the top and high frequency light on the bottom. And each of these different pictures tells us where something else is. So the low frequency light tells us where the gas is. Sort of infrared light tells us where the dust is. I'll talk about dust more in a little bit. And then the optical and ultraviolet light tells us where the stars are. And then X-ray and gamma ray tells us where the really extreme stuff is, like the accretion disks of black holes and stuff running into each other. And so we can actually look at all of these using different instruments. The VLA is made to look at gas. ALMA is really good at finding dust in galaxies. HST is really good at finding stars, and Chandra is made for X-rays. So kind of like the city, you need all of the different frequencies to tell what's going on. In astronomy, we need all of these different frequencies, but we also need all of these different instruments or telescopes to see all the frequencies. So that's why we have so many telescopes. Right, so that's all that. And now we can talk about dust, since that is one of the main words in this talk. So to talk about dust, first we're going to talk about fire. So fire is pretty easy. You put in wood, you have a fire, and what comes out is smoke or ash. And the same sort of thing is true for stars. If you put in gas in a star, then you get dust. It's a little bit more complicated. You get gas into stars, it gets fused into heavier elements, and then gets sort of collides with each other into heavier, larger particles, and then gets expelled by like coronal mass ejections or when the star explodes. But for now, we can just think of dust as the ash, the byproduct of stars burning gas. So in order to see dust, we have to have a lot of stars that are burning gas. We have to have stars for a while. So this means that if we look in the faraway universe, in the early universe, there really shouldn't be that much dust. So these are 10 pictures of galaxies as they were when the universe was only 1 billion years old. So this is pretty early universe stuff. And here the red contours are showing where the young stars are. And with these contour plots, the more contours there are, the higher the intensity. It's sort of like a topographic map. So you can think of this as like a big mountain. So you can see that all of these have a lot of these red contours, so they have a lot of young stars. So they're making stars, that's cool. But not many of them have blue contours. There's only these two that have a few, and then these have really small ones. And these blue contours are showing us where the dust is. So that means that when we're looking at these galaxies in the early universe, we're not seeing that much dust, which makes sense because there hasn't been much time for the stars to burn the gas to make the dust. So that's sensible. But there are some sources that have a lot of dust. So this is another source that's a little bit closer to us, a little bit farther along in the history of the universe. It's only 1.3 billion years after the Big Bang. And this one's really cool because we have two really big galaxies, and then we have two really small ones that are interacting with both of them. And here, these white contours are showing us where the dust is. You can see there's a whole lot of dust. And the sort of yellow background light here is showing the visible light. So even though these are galaxies in the early universe, we're seeing a whole lot of dust in these guys. So the question is, why do we have so much dust here? And it turns out that by looking at the other properties of these galaxies, we can tell that they are making new stars incredibly fast. So the Milky Way galaxy, if you add up all of the new stars that it makes per year, you have maybe 1 or 2 times the mass of our sun. It's reasonable. For these galaxies, each one individually, you have over 3,000 times the mass of our sun. So they are star factories. And they've been making stars this fast for a while, and they didn't start yesterday. So that means that they have had a lot of stars from very early on and have been burning gas for a while, so that's why they have so much dust. So if you think of the galaxies in the previous slide as just regular campfires, these are sort of campfires that you pour some gasoline on, except they keep burning for a long time. Or maybe they have much bigger wood piles. Maybe that's not a good analogy. But yeah, these are kind of exceptional sources. We can look at another object where here this is just showing the emission or the light coming from warm dust. So this is showing where the dust is in this galaxy, a different one that's a little bit closer to us. And here we have a bright central galaxy, and then these two little things coming out here. And yeah, based on this study, they think that this is actually 3 colliding galaxies. So we have a big central one, and then we have 2 smaller ones that are running into it. And yeah, as we saw in that cool simulation, it's really common for galaxies to run into each other. So this would make sense. And based on some other studies, we think that as galaxies collide with each other, that causes both of them to make a whole bunch of stars because the gas gets denser and kind of mixes it together. So here there's a lot of dust because they're colliding, which is pretty neat as well. Cool. So this is my second to last slide here, but I've been talking about the distant and dusty universe, but some of you might want to know more about the close by and dusty universe. So this shows a night sky view of the Milky Way right now. So if you were to go out to New Mexico or something and look up, you would see this really nice disk here, this nice straight line, where the white is the stars and the brown here is the dust. So the dust blocks the optical or the visible light from the stars. But back here, you have the Andromeda galaxy, which we talked about is 2.5 million light years away. But the thing is that the Andromeda galaxy is coming towards us at around 300 kilometers per second as we speak. But it turns out that it won't actually collide with us for 4.5 billion years. So you don't have to set any alarms about it. So the rest of these panels are going to show what the night sky will look like as the Andromeda galaxy gets closer and collides. So if we fast forward 1 billion years, Milky Way is pretty much the same. Andromeda is a little bit closer. Fast forward another 2.75 billion years. Andromeda is huge. We can see all the visible light from the stars. We can see the dust lanes here. And then if we fast forward another 100 million years, then the two disks of the galaxies have collided. And I don't know if you've seen these simulations, they're really cool. There's a lot of them on YouTube. But when two disk galaxies run into each other, it's not just like two frisbees hitting each other and bouncing off. Because they have so much gas and stars and dust and everything, they kind of meld together and bounce off each other, and all the stuff inside them really mixes up. So when Andromeda runs into the Milky Way, the night sky view is going to be amazing. So here, all the white light is the stars, all the sort of brown is the dust. But here we have all these little red spots, which are really hot areas of gas around brand new stars. So as we talked about, mergers or collisions of galaxy cause a lot of star formation. We'll be actually able to see these new stars. We can fast forward another 50 million years. Things will be even crazier. You can see all the brand new stars, all the older stars, all the dust. It's crazy. And then another 100 million years, and things are surprisingly calm. And this is because after these two galaxies collide and are really messy for a while, eventually they'll sort of settle down and sort of just gravitate into each other. And so we have a much nicer view here. And then these last two panels are pretty far in the future, 1 billion and 2 billion years after. And yeah, we can see that these really complex hot stars and dust and everything really just calm down into a sort of boring double potato and single potato sort of object here. And this is because all these simulations have shown that when two disk galaxies run into each other, instead of forming another disk, a lot of times they form what's called an elliptical galaxy, which is just like a big potato full of stars. So the night sky in 7 billion years will be boring, sad to say. And since some of you might be wondering, the sun is expected to expand into a red giant in around 4.5 billion years, and it will engulf the Earth. So these last two panels are actually from a alien world somewhere. Maybe they're from Mars, not from Earth. Cool, so that's what I got. So just in summary, we talked about how space is ridiculously big. And if you start driving a car in space, you're not gonna get anywhere for a long time. We also talked about how when we're looking at these super far away galaxies, we're seeing light that's been traveling for a long time, so we can see the universe as it was in the past. Talked a little bit about dust and how it's pretty much just the ash of stars that are burning gas. Then we looked at some pictures of these galaxies as they were in the early universe and saw that some of them have dust and some don't. And the ones that do have dust, they do because there's lots of stars. So yeah, thanks for your time and happy to take any questions.
Wonderful. Thank you so much, Gareth. Really, really fascinating stuff. I love the phrase, a big potato full of stars. So yes, anyone that has a question for our speaker, stick them in the YouTube chat, which is down this way. I think it's down this way. I always point to my left. I think it's down that way. First question from Julia, who just wants to talk a little bit more about the timescales. So will the sun have died by the time the Milky Way and Andromeda start merging, or will they be happening at the same time? Or
yeah, so it's I'm not quite sure, because I've always heard that the Andromeda galaxy will collide in 4.5 and the sun will expand in 4.5, but I'm not sure if it's 4.5, maybe plus or minus a few 100 million years. So yeah, I mean, in this simulation, it looks like the sun will expand sometime between these two. So, the rest of these may actually be visible from Earth. The sun may still be in its current, yellow dwarf phase.
Yeah, it's often a really good point, right? That's with astronomers, we have these big uncertainties. And so a factor of 100 million years is maybe not that much for an astronomer. A question from Nuno, who wants to talk about the universe's expansion. They've heard this idea of 72 kilometers per second per megaparsec. Can you just explain a bit what that means?
Yeah, so that's a tricky one. So the concept you're talking about is that as we look farther away, so if we look at the light from galaxies that are a few million light years away, then we can the farther away we look, the faster away things are moving, basically. And this is partly an effect of just the expansion of space. I admit that this is something that should have been covered in my cosmology classes that wasn't. So, I mean, it's kind of cool because as we look at these faraway objects, we actually use the fact that these farther away things are moving away faster as a way to figure out how far away they are and how long the light's been traveling. I can't really comment on why that effect is there, though.
Wonderful. Thank you so much, Gareth. It looks like there's no more questions. I think everyone is everyone contemplating the deep meaning of the sun expanding and the weird future. So thank you so much to Dr. Gareth Jones. Thank you to all of our speakers that have given their time to give us public talks this season. We've really had a wonderful time since October learning about all these things. Thank you to our observers who are not here tonight because it's still sunny outside, but the Cambridge Astronomical Association, the amateur astronomy group that have been helping us with these evenings for decades now, have adapted really, really well and taken these things online and streamed so much really nice live stargazing for you guys. So thank you to everyone that's helped. Thank you to you guys at home. And yes, we shall see you in October.